In this video, we'll begin our discussion of derivatives of vector functions. The great thing about this, recall from Calc 1, I'm going to show you how this works by using the definition of Calc 1, which I know you guys loved probably at the time. I would recommend looking over that definition again now that your mind is a little more math mature. I would recommend looking at the derivative function, definition again, because typically what happens, and this is easy to understand, but you go further in math and you look back and things get easier. So I would recommend maybe looking back at your definition just to help with your understanding of calculus as a whole. This can be extended to vector value functions. I'm going to work this out and then we're going to make sense of how it works out. So if I use the definition of my derivative, this is just the difference of my y's, right? With change of t being the difference between my x's and then dividing. So really what this is this is a slope formula, right? The y's on top, my output's difference, and then on the bottom is the change of t, which is my x's, the change of the input variable. All we're doing is that slope, but if I throw this limit into it, remember it brings our 2 points together, finding our instantaneous change, or the tangent line. So it being a tangent line, we can apply this to our vector value function and call it a tangent vector. Okay, so let's run through the definition of this so you can see where it comes from. And then we'll do an example. Okay, so let's start with r of t prime is going to be equal. Okay, it's going to be the limit. And I know that how this works is all those parts are going to be plugged in to the function itself. So what this means, what we're going to end up with is plugging that into each part. So let's do that. Okay, so plugging in that to x, y, and z, sorry. So here's my fraction bar. So this is going to be a bit of a pain. I'm going to have x of t plus delta t. And then remember, this is a I, j, and k. This is a vector. So plus y of t plus delta t, j, plus z of t plus delta t, k. And then we're going to keep going now with the minuses with just t in there. So I got minus x of t, I, minus y of t, j, minus z of t, k. This is all coming from that. This says to plug it in, so we did. Let me extend my fraction bar here. So there is the top, and then the bottom is just going to still be delta t. Oh, and I did exactly what I told you guys not to do. We need to write our limit. All right, so as the difference of my t's go to 0, bringing in my secant line to my tangent line. Now I'm going to regroup this. Change of t goes to 0. And I'm going to create 3 functions here. From what I had up there. And we're going to multiply these 3. Okay. So I could put my x of t plus delta t minus, we're not going to put times, sorry, we're going to put plus in between. I know what I can do with these is I can throw them together with my I. So what I'm going to do, sorry, I'm changing so much, but I'm trying to make this make sense and look pretty for you so you can make sense of it later. So I grouped my I's together like that with a delta t plus, right? You can imagine what I'm probably going to do here is I'm going to put all my J's together. So that's the Y's, y of t plus delta t minus y of t over delta t. We keep the delta t's because if I'm just adding them, then we keep our denominators. We don't change it. And then the last thing is going to be the k components. So that's going to be z of t plus delta t minus z of t over delta t. Notice if I add all those 3 things back together, I get the line above. Now this limit is being applied, and we know from our studies of limits with vector value functions that the limit just applies to all three. So how this is going to end up is we have the limit as delta t approaches 0 of, and I'm going to be lazy here. I'm going to copy this. Sorry that you can't do the same unless you're on a same type of thing. This is my I component plus the limit as delta t approaches 0. And I'm going to go ahead and duplicate the y's too. All right, that goes in there. And then let me scoot this over because I ran out of room. All right, plus, and then the last thing, we have our limit as approaches delta t approaches 0. And then we have our z. All we did, is, in a way, is because we know we can, we distributed our limit. Let me shrink this down just a bit. All right, I know this is the k component. So what the heck does this mean? Well, that means r of prime of t. Well, if I look at each component, the thing that's in front of I, oh, we need our hats. J and K. There we go. Forgot my J there, so hopefully you put that in. Is each set of parentheses is just the definition of the derivative for that function x, for that function y. So this is actually just equal to x prime of t I plus y prime of t j plus z prime of t k. What does that mean? Okay, well, that means that if I want the derivative of a vectored value function, all I got to do is take the derivative of each part. We proved it. We just showed that by the definition, I can rearrange things and show that if I just want the r prime, I just take x derivative for I, y derivative for j, and z derivative for k. So we have a vector coming out of the derivative, not a scalar. This vector still describes that same thing. It's the tangent. It's the growth in what direction. And the good thing is about a vector is it not only gives me the slope like a derivative would, it gives me a magnitude which describes the length of how far we're going, and then a vector that describes the direction, right? The xy or the xy and z components that will give me the direction. So it's a pretty powerful tool if we're working with vectors. So let's find a few examples of this. This will just be really a derivative review. So r prime. What I would recommend actually is doing what we did for limits, because some of these are going to get really gross, and I don't know about you, but I don't want to rewrite the vector every single time. So what I mean by that, okay, x of t, I write down what it is. Okay, it's t cubed. And then I go ahead and show my derivative. Okay, well, if that's what that is, the derivative is the power rule. I bring it down, go by one, down by 1. Same thing, y of t. I like to write it here, t squared. And what this is going to allow me to do is give you a lot of partial credit if you mess up just one of them, right? If you don't do this type of thing, it's kind of hard for me to catch it all. This is going to be your fairest way. And to be honest with you, I used to not show these little parts just as a student, and I would make a lot more mistakes not showing them. I know I sound like the teacher in the room, surprise, right? But showing these steps very clear will keep you underwhelmed. Especially as our problems, as we go on through the course, the problems are going to get much longer. Okay, so z of t, that was equal to minus t, take the sign with it. So z prime of t is equal to -1. So what we just answered, r prime of t, is equal to 3t squared I plus 8t j minus k. That is our tangent vector that points in the direction of any point in t. Like if I wanted to know that tangent vector at point t, I just plug in the value. And it will give me a vector that the curve is moving. And it will give me how much, the magnitude, and then the vector describes the direction. All right, I have a few more here just to kind of go over some rules. I'm going to rewrite this. Okay, first I label. Oops, did z, y of t, and then z of t. Okay, x of t is going to be, that's -3 over t. This is one I would recommend just memorizing. It shows up a lot, but I'm going to show you the way to go about it that we did in Calc 1. I bring the power up. This tells me x prime of t is equal to 3t to the negative 2, which is 3 over t squared. So what I do anytime I have something over t, I know it's over t squared and I change the sign. That's what I have memorized. You can go through the process we just went through every time. There's no problem in that at all. Y of t is negative 1, so that means y prime of t is 0. And then we have one more here, ln of the square, oh, let's write z of t. Z of t is equal to ln of the square root of t. I'm going to rewrite that as ln of t to the 1/2, right? And then now we get to find z prime. This is a chain rule. So I got 1 over t squared, or sorry, t to the 1/2 times the derivative of the inside, which was t to the 1/2. Actually, let's do this because I think that's a bit confusing if you look at it later. There we go. 1 over t to the 1/2, even though it meant the same thing. And then we take the derivative of the inside. So the 1/2 comes down, and then I got a negative 1/2. This is going to give me 1 over 2 to the t. The t to the negative 1/2 goes 1 down, adding a 1 with that other t to the 1/2, and then a 2's on the bottom. So that means r prime of t is equal to, I'll do it in component form this time, 3 over t squared, 0 always, okay, and then 1 over 2t. So there is our tangent vector given any t, given the function r of t above. All right, we're going to do one more that's going to have some heavy product rules and some chain rules. I just want to make sure we're getting some review. Again, you're expected to have your derivatives down at this point. So if you need to go review, you have a book that Calc 1 was taught out of that you took, please review. You can find derivatives online. If you need help directing where to go, professors I actually use, and a lot of my notes come from, is Professor Leonard and some other people. Just reach out to me. I can give you some sources if you need. All right, we have one more problem to go over here. These are going to get a little heavier. We got x of t, y of t, z of t. All right, so let's begin this process. X of t is negative e to the negative t squared times sine of t. All right, I'm going to write out the power rule here. I'm going to go down because we're going to probably need the room. So the power rule looks like this. D dt of the first function, and you may think about it different, and that's okay. If you remember it, that's all I care about, times the second function plus the first function times the derivative of the second function. You do not need to write that out every time. You can go ahead and just do the derivative. The chain rule, you don't need to show this step. If you're struggling with remembering the power rule here, then, and we should write that power rule, then I would review. Again, go back and check out the power rule. Write it out this way every time if you're confused. All right, this one is a chain rule. The derivative of e to the something is e to the something. So I get exactly what's there, and then I times by the derivative of the inside, which is a negative 2t times sine, that doesn't change, minus e to the negative 2 of t, negative t squared. The derivative of sine is cosine t. Notice that I can actually factor out negative e to the negative t squared. With that negative, let's do that. That's a positive. No, I think let's just clean it up. 2t e to the negative 2t squared times sine t. I thought I could factor some stuff out, but it's really not going to make things cleaner. So I'll just write it. Negative t squared cosine. That is a great answer. We could factor out the e, but it really doesn't change anything for us. Okay, y of t is equal to negative tangent to the negative 1 of t. This is one I would recommend memorizing. It's going to show up quite a bit. So this one is y prime of t. And this is negative 1 over 1 plus t squared. I'd get that memorized. That's going to show up a lot in DiffyQ if you have to take that. Okay, and then z of t is equal to negative 1/2 e to the negative t cosine of t. So this is, again, another power rule. So I'll write this out. Let me add another page to this. Boom. Okay. So z prime of t is the derivative. I'm going to write it all out just for the sake of notes. Negative 1/2 e to the negative t times cosine of t minus 1/2 e to the negative t times the derivative of the cosine, the power rule. All right, this is equal to, okay, we get the same thing, but the power, we take a derivative of negative t, is going to be a negative, so we get 1/2 e to the negative t cosine t. And then minus, I keep 1/2 e to the negative t. Derivative of cosine is a negative sign, so I'm going to do that. This one I think I do want to clean up. I can take 1/2 e to the negative t out times cosine t plus sine t. I can't replace the inside with anything. They have to be squared to use that identity, so if you're ever thinking, I can replace that, no, you can't. Okay, so I'm going to leave, I have all three parts, so the derivative for my vectored value function is, I forgot what x was, oh, it's right there, 2t e to the negative t squared sine t minus e to the negative t squared cosine t, comma, negative 1 over 1 plus t squared. And then the last component, let me move some things over, is going to be, I'm going to be lazy here. I know you can't do it, but I can. I can duplicate, and I'm going to throw that there, make it a little smaller. There we go. And there is my third component. There we go. So that is the tangent vector, or just the derivative of a vectored value function given a random t. It's nasty, but we can do it again if you need to review your derivatives. They're not going to go away. This is calculus. We're going to do a bunch of derivatives and a bunch of integration. So please go review to make your life better. I'm not going to throw anything crazy at you, but what we just did is fair game. I don't consider what we just did anything of difficulty. Anything like this, like memorizing that to that, you will get a table at this in this semester, but I need you to get them down. It's time to actually get your calculus memorized to a point of effectiveness, knowing that you're going to have tables when you go into your field. You'll have the internet, but it will be better if you understand some of them. You need to be able to memorize a few. You'll appreciate it much more.